IL sine theta. You know, we have said all this. This is your what? Your magnetic field. Your I is your point. Your L is the length. Force on a moving charge in a what? A magnetic field. You understand? This is just the general force under electromagnetic field. Now, force on a moving charge. Now, what is the formula for the force on a moving charge? We have what we call your QVB sine theta. Hope you are saying it. So that will be the force on the moving charge. Now let's look at this particular question. The example there says a force F is on a charge plus 2Q plus 2 microcoulomb. Moving the velocity of 2 times 10 to the power 6 meter per second. That's the velocity. Remember, our formula is QVB. Now it has a magnetic field in a field flux. That's a field flux density 0.5. So that's your B, 0.5 Tesla. Then calculate the force on the field. So we are looking at F, which equals what? QVB sine theta. Now look at those two statements. Says number one, when it is parallel to the field. If it's parallel to the field, your sine theta, I mean, this will be sine 0. And what's before you go into your force will be what? 0. Hope you are getting it now. But when it is perpendicular to the field, you have your sine 90. Your sine 90 is 1. So from there, your F QVB sine what? 90. You just insert those values. Your Q, which is 2. That's 2 exponential minus 6. So you just insert your Q here. Your velocity, which is where's the velocity? Yeah, 2 exponential 6. You put it here. Then your what? Tesla 0.1. You put your 0.5 Tesla, you put it in here, and you want to compute to be able to obtain. Let's go to your electromagnetic flux induction, this new subtopic. Now, under our electromagnetic flux induction, what are we talking about? We are trying to induce. Induction means to fix something in. We are trying to induce. So, when you now have electromagnetic induction, you are trying to induce flux. You understand? In a what? In an electromagnet. What is an electromagnet? An electromagnet is what? Any material that has the effect, that has properties of what? Electrical material and what? Magnetic material combined to be one. So that particular type of material is an electromagnetic material. So at this junction now, this is what we are trying to do. We are trying to what? Induce. You understand? Induce flux. You understand? Now you want to induce electromagnetic properties in terms of flux into what? A part of a material. Now if you check out the diagram we have there, that diagram is actually a diagram of a transformer. Look at, if you have something like this, if you must be going through the transformer that is actually being placed in your house or at your street, this is just what it entails. We have what we call the step down transformer, and we have what we call the step up transformer. So if you have something like this, now this region, from the diagram there, we have what we call your VA. Now at the diagram here, at this other junction, you have your bulb here. Now it's going to light up your bulb. Now this is when the what? At this region, flux has now been induced. Now immediately flux is induced, it will what? Bring out current, electricity. Now at this junction now, what do? We need to understand what we're actually talking about before you analyze this one diagram. Now let's continue. Now if the magnetic flux through a coil is altered, then an electromagnetic force will be what? Generated in the coil. Now Faraday discovered that EMF must be what? Could be what? Generated by one, either moving the coil or the source of the flux relative to each other, or two, changing the magnitude of the source of the flux. If you have two magnets, let me say you have something like this. I want you to understand what this particular topic is talking about. Now, you have your north here, you have your south. There is tendency for these two magnets to attract. Right? Now, you now decide to take a coil. This is a coil. If I say coil, if you want to know what a coil or what coils are, just go through the internal section of your radio. You understand? You see a particular body. We used to call it a transformer. It's like this. They will wind it this way, whereby this particular one is probably let me say orangish. I think it's orange. The color should be orange. Now it's being wound across a particular body. Now this particular body is grey. This section is grey. Then we have this as orange. Now any particular object you see in your radio or any material, any device you are using, just lose it and see. You see that that type of material is called a transformer. What does it do? It tells you what? Reduce the total voltage that is coming into your device, so that the device doesn't get burnt. If your transformer in your device is not working, then heavy voltage will be coming into your device and you can burn it down. So the function of the transformer is to help to what? Bring down the incoming voltage in your device, so that it doesn't get burnt. Now let's come back here. So since you now get the actual color of a coil now, so it is those type of coil that will actually be used to what? Make this particular object here. Now what's the function of the object? Let me give it to you so that you understand. Even in the invisible connection I spoke about, that's your flux. We call it magnetic flux. It is without flux that two magnets will want to attract. Now when you now have a coil in between, now what does this coil do? It's trying to cut that flux. Now when you put two magnets together and you put a coil in between to rotate, you understand? To rotate it, to actually cut this flux, two things are involved. Fleming is one. Fleming, there is a scientist who called Fleming. He's one that devised Fleming's left-hand rule. It's a law too. You understand? Fleming's left-hand rule and Fleming's right-hand rule. You understand? Now when we get there, we are going to expatiate on it. Now what are we saying? When you use this coil, you turn it in terms of motion to cut this flux. Two things are involved. You are cutting flux. Do you understand? At the same time, you are running motion. You understand? I'm not talking about you moving on both directions. Let's say you are moving clockwise. You move this coil clockwise and it moved. By the time you move it continuously, the flux you are cutting here, two things are involved. EMF will be generated. PD, potential difference will be generated because you cut this flux. Now if you continuously cut the flux, potential difference will be generated, and before you know it, this potential difference that is generated will fall back to the movement of this coil, thereby making this coil to continuously rotate. You know, if this is to be your generator, this is probably the rope you wind. You understand? Now maybe you wind, what you are actually trying to do, you are inducing inside the mechanical structure of your generator. There is what we call the magnets. You understand? The magnets, they've been designed in such a way that you have a coil in between. Now this coil is what we call the rotor. It rotates. While these two bars of magnets are what we call your stator. Your stators are always permanent. Your rotors rotate. In some design, it is it is the coil that is static. You understand? The coil is static, is stable, while it is the magnet that rotates. Whichever way, by the time it rotates, voltage will be induced at the end of this coil. Now the voltage that is induced will now come back to actually make constant the movement of this of this coil. So immediately there is constant movement of this coil, two things are involved. PDF is being generated and a backward motion is actually being generated from this coil. From there, EMF will be induced. When we proceed, you will definitely understand what I'm actually trying to say. From that, at this junction, it will still be looking like magic. But when we proceed, and you'll be able to get how your generators is actually being designed. Like in your generator now, there are two sections. We have what we call the mechanical section, and we have what we call the electrical section. It is in the mechanical section that you put your fuel. You understand? Whether it's diesel Shey get whether it's diesel or your PMS. That's what we call petrol. Shey when you put your diesel, you put your fuel, you make sure you check your oil. That's your lubricating oil. You understand? Now all you just need is for what? Is to allow movement of what? This what? Mechanical section. You know the rotor here. You understand? In your what? Mechanical design. What you just need to do is to make sure there is constant movement. Now a belt will now be tied. You understand? It will be connected to the electrical section. Now at the electrical section, what do you have? What they call it is alternator. You understand? You have the alternator. So it is in this alternator that what? PDF. I mean, potential difference is being generated. Now the volt that comes into your house for usage is being generated by the alternator. But what actually brings about the motion is the mechanical section. So the belt will now rotate. So the mechanism in this alternator is what I'm actually trying to explain. What you have in your generator, you have your coil, you have your magnets, and you have your what? Current brushes. We call it current brush. Now those brushes are the ones that help to what? Generate those potential difference. So when the potential difference is now being generated, it will now send it to your to the little transformer, which now what? Try to regulate, which is now being sent for what? Consumption. So these are what we're actually going to be looking at in this section. So just relax and see how they are all being broken down. Now note, EMF is only produced while the flux is changing. Remember, EMF will only be produced, that's the potential difference, will be produced at this section because the flux are what? Changing. In this alternator, there is what? There are magnets which who want to what? Always attract. But there is a coil in between that breaks that force of attraction. That's the flux. So that EMF will not be what? Produced. Let's proceed. Now, let's look at Faraday's